Hello, welcome to Unit 5, Lessons 3, Representing Exponential Growth. The learning objectives for this lesson are to be able to explain the connections between an equation and a graph that represents exponential growth, and to be able to write and interpret an equation that represents exponential growth. So in Lesson 1, we looked at the difference between linear equations and exponential equations. We talked briefly about how we could represent those exponential situations mathematically. And then we made general observations about how exponential graphs look differently than linear graphs. So let's take a look at the first activity. So in this first activity, it says to rewrite each expression as a power of 2. So I'm going to do the first one for you, and then I want you to pause the video and see if you guys can do the next 3 on your own. So for this activity, you are going to have to reference back to your exponent rules that you did last year in pre-algebra. Know that whenever we multiply with the same base, you can just add the exponents. So for example, I know for this problem, I'm going to add 3 and 4 because I'm using multiplication. So I would have 2 to the 7th power. So go ahead, pause the video, and try the next 3. All right, for the next one, since the second number does not have an exponent, we assume there's a 1. So this would be 2 to the 6th power. And with multiplication, we know we add. Division, we would be subtracting. So 10 minus 7 is 3. So that's 2 to the 3rd power. And then again, for the last one, since we know the 2 has an exponent of 1, this would be 2 to the 8th power. All right, let's take a look at the next activity. So what you're going to do, question 1 asks you to complete the table and take advantage of any patterns you may notice. So go ahead and complete just this question, and once you're done with that question, check your answer, and then I'll have you go on to questions 2 and 3. All right, so for question 1, I know that when x is 2, that's going to be 3 squared, which I know is 9. And then when x is 1, that's 3 to the 1st power. That's going to be 3. Now the patterns you may or may not have noticed is that each time we are dividing by 3, right? 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. So if we were to continue that pattern, we would also do 3 divided by 3, which gives us 1. So now that you've had this table filled out, go ahead, repause the video, and answer questions 2 and 3. All right, so question 2. For question A, what does my question mark need to be in order for it to become, the full thing to become 9 to the 7th power? So in other words, what plus 7 equals 7? So I know that's just going to be 0. And then the same thing for B. What 12 minus what will give me 12? That's also 0. So question 3, what is the value of 5 to the 0 power and 2 to the 0 power? Well, in each case, we know that those are going to be 1. All right, let's take a look at the next activity. So in this activity, it says the biology lab, 500 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. So for the first part, it wants you to write the expression to show how to find each number of bacteria. So you're not actually multiplying, you're just writing out what you would multiply to solve this. Then from there, you're going to write an equation, and then from there, you're going to use the equation to answer the question when t is 0. So go ahead, pause the video, and attempt that on your own. All right, so for the first one, I know that the bacteria started at 500, and I also know that it's doubling each hour. So to figure out after 1 hour how much there is, I'm just going to do 500 times 2. Now, for 2 hours, I have to take my previous number of bacteria, which would be 500 times 2, and then double that. So I just write that as 500 times 2 times 2. Okay, for 3, the previous one is going to be doubled again, so that gets multiplied by another 2. For 6, I know I'm going to be multiplying by 2 6 times. So basically what's happening here is that I'm taking 500 and I'm multiplying it by 2 to the t power. So whatever t is, whatever hours are, I'm going to raise the 2 to that power and multiply it by 500. So my equation is just going to be n equals 500 times 2 to the t power. So now let's go ahead and calculate when t is 0 what that would be. So if we know that t is 0, so that's our starting point, that's going to be 2 to the 0 power. Well, 2 to the 0 power is just 1, so that's 500 times 1, which we know is 500. So this represents the number of bacteria at the starting time. So 500 is the number of bacteria at the starting time. All right, question 2. In a different biology lab, a population of single-cell parasites also reproduce hourly. An equation which gives the number of parasites p after t hours is p equals 100 times 3 to the t power. Explain what the numbers 100 and 3 mean in this situation. So go ahead, pause the video, and answer that question. All right, so in this situation, it kind of mimics what we were talking about in the previous one, where 500 was the starting amount. But in this case, because it's 100 times 3 to the t power, I know that there are 100 parasites to start with. And whereas our previous problem doubled every hour, this time the parasites are going to triple every hour. So the 3 means the number of parasites will triple every hour. So if we think back, we in this problem, we were having a pattern of something doubling or something tripling every hour. This is defined by a set of common factors because each time the hour increases by 1, the number of bacteria is multiplied by the same factor. So either 2 for the first problem or 3 for the second problem. If we were given another situation where the starting number of parasites was 80 and the population quadrupled, that expression would then be 80 times 4 to the t power. So we have our starting amount, and then we have how much it's increasing or how much it's being multiplied by each hour. So this is amount being multiplied. All right, let's take a look at 3.4. So in 3.4, it's asking you to now graph the situation that we talked about in the previous activity. So you have 2 different graphs. The first graph is talking about the number of bacteria. So one is bacteria. And remember, bacteria started with a population of 500 and it doubled. For graph B, this is the parasite problem. And our parasite started with 100 and it tripled. So go ahead, pause the video, and graph the situations for 0, 1, 2, 3, and 4 on each case. And then you have a couple of questions that you have to answer afterwards. So answer questions 2 and 3. All right, so let's go ahead and graph these situations. So I know for my bacteria problem, we started with 500. So my 0 hour, or my starting point, or in this case, my y-intercept is going to be 500. So that's this point right here. For after 1 hour, I know that amount doubled, so it went from 500 to 1,000. And then after 2 hours, that amount doubled, so from 1,000 to 2,000. And then after 3 hours, 2,000 doubled, so that goes all the way up to 4,000. Oops. And then after 4 hours, that was it was all the way up to 8,000. So that's right there. For my other graph, we started at 100, so that's going to be a little bit lower. So probably about there. After 1 hour, it tripled, so it went from 100 to 300. So that's going to be about there. And then it went from 300 to 900, so that's about there. Then it went from 900 to 2,700, because 900 times 3 is 2,700. So that one's going to be about there. And then last, for my 4th hour, we would have 8,100. So that's going to be all the way up here. So about there. And I gotta move my other one over. I just realized. Let me fix that. Okay, so it's gonna be right there. There you go. That's better. Alrighty. So on graph N, which is the bacteria one, where can you see each number that appears in the equation? So our equation, if you recall, was 500 times 2 to the t power. So the 500 is the vertical intercept, or the y-intercept. And the 2 is the doubling of n as t increases by 1. And then the same thing for the second graph, my parasite graph. So that was 100 times 3 to the t power. So for this one, again, the 100 is the vertical intercept. And the 3 is the tripling of p as t increases by 1. Now, another phrase for the 3 and the 2 in this case, we can also call this the growth factor, right? So 2 and 3, these are growth factors. It's the amount by which how quickly the graph increases. So key takeaways here is notice the starting point is always the vertical intercept, and our base for our exponent is always the growth factor. So in this lesson, we defined that term, growth factor. We also used equations and graphs to represent situations that change exponentially. So we looked at situations similar to this. So suppose a population of cells start at 500 and triples every day. The number of cells can be calculated as followed. So we're doing the original amount, 500, times 3 to the d power. If we were to graph this, the 500 would be our y-intercept. And the 3 represents the growth factor. Okay, we also talked about how anything raised to a 0 power is always going to be equal to 1. And that's just because that's our starting point, right? If we are on day 0 or hour 0, that means we're starting at that amount. So we need it to be multiplied by 1. So it kind of makes sense that we're raising it to the 0 power and saying it equals 1. So that's it for this lesson. Go ahead and start working on the cool down. Thanks for watching.